Hello and welcome to the new session of group multiplication table. Dear friends, this is the part 2 in connection to the first. I am again your instructor Saurabh and let's begin for this work. In earlier series, we have seen that how group multiplication table can be constructed in connection to the group theory. So a group multiplication table consists of h rows and h columns. They are labeled with a group elements and so is each row. The entry in the table under a given column and along a given row is the product of the elements which had the column and that the row. So let's take the multiplication table in the order that first go for a row element followed by a column element. That depends upon the choice you just fix up. And thus at the intersection of the columns labeled by x and the row labeled by y, we find an element which is the product xy that has the value of z just as shown in the coming table. And obviously the element under questions should belong to the set. So if a table has the rows and column as indicated, the product would be indicated the way in this table has been shown. And this is governed by an important point which states that each row and each column in the group multiplication table list each of the group element once and only once. Now that practice is very typical, very peculiar, that there is no repetition in the elements along a row or a column. From this, it follows that no two rows may be identical or no any two columns may be identical. So there is no question of an element getting repeated in a row or in a column. That is a broad idea that we understand about a group multiplication table. Let us just begin how a theoretical group of order 2 would be constructed. If there are only two elements, E and A, then we can have E and A written on the row and column. Their product would be there in the first row and the first column, and the last element is left with no other choice than only the identity, because we believe that there has to be no element repeated in the row and column. So this is the way, or rather the only way, in which a G2 group of order 2 can be constructed. If you talk about the group of order 3, there are some problems. See, if I take this group EAB, EAB, and write there first row and first column as it is, then there is a problem in deciding what would be the other things. If I believe that AA is equal to B or AA is equal to E, then the product cannot be assigned in the way that we do. If we assume AA is equal to E and BB is equal to E, what would get? What will get? EAB, EAB, EAB here, EAB. Now we are assuming AA is equal to E. So this is the E and BB is equal to E. So the diagonal elements are E. Now if we keep the diagonal elements equal to E, the point is what should be written at this juncture? What should be written at this point? Because we have set the diagonal elements as E. Now if I write B here, then B and B would be repeated. And if I write B here, then again B and B would be repeated. So this way, assuming that each element is reciprocal to itself, is not a justified way, and therefore this method of writing a group multiplication table for order 3 is seemingly incorrect. However, there is another way of writing this group, that is, if we assume that EE is equal to E and A is equal to E and BB is equal to A, and if you write like this, so the product is something like this. You have EAB, EAB, and now what we are assuming here is A is equal to B and BB is equal to A. So if we do it, if we are assuming AA is equal to A multiplied by A is equal to B and BB multiplied gives A, then there has to be a right order. So A is B and BB is A. So that's the postulation of a cyclic kind of group. So that is the only way in which we have a group of order 3 can be constructed. However, if we talk about the group of order 4, then there are possibilities. Either we can write in the method of cyclic group or simply in another form. A cyclic group of an order n is defined as an element x and all of its x powers up to x power n equal to e. An important property of a cyclic group is that they are abelian. It's an important point. Cyclic groups are abelian. So this must be so since the various groups elements are all of the form of x to power n or x to power m for all values of m and a. So this G2 is an abelian group and also a cyclic group. When you talk about the group of order 4, the concept of writing a group of order 4 in terms of a cyclic group is we assume that x is an element that is equal to a, x square is equal to b, x cube is equal to c, x 4 is equal to e. If we do so, then making this table would be rather easier. So if I write the elements in a row and columns and put the values, the first row and first column is of course same. Now the next element, if I'm looking forward, AA is equal to what? So AA will be equal to B, because x square is equal to a, so a square is equal to b. It means a cube is equal to c. It means a to the power 4 is equal to e. So when you're talking about b into a, so here is b and here is a. So b is actually a square and a is a. So this becomes a cube, and a cube is nothing but c. So this is c. And similarly, if you talk about e, the last element, c into a. Now if you talk about c, c is equal to x cube, that is equal to a cube, and a is a. So it is a to the power 4, and a to the power 4 is nothing but a. So this is a very direct kind of situation where we can write the elements in the form of only one element as depicted here. Now predictably, if we talk about a into b, so a is a, b is a square, so here it is the a cube. Now when you're talking about a cube, that means that must be equal to c. So the next element should be here c, and the other element, that if you talk about a and c, a and c. So a is a and c is of course a cube, so it's a to the power 4 and e. On the same analogy, the other elements can also be substituted and we get a complete form of this group multiplication table. So the cyclic group is a method in which one element can be depicted, one element can be chosen to represent the entire group multiplication table. If you go further for another method or another view of making a group multiplication table for the same, there is another possibility that you can use the elements first as such in a row and column and believe that all the elements are now diagonally set up. So when I do like this, then fortunately if I write E here, that is A is reciprocal to itself, so I have left with no other option to put C and B here. So the C and B I can substitute here also. Now if I believe that B into B is also the E equal to E, so if I believe this is E because B is reciprocal to itself, then the last element, the only possibility left is A, because A is not getting repeated so far. And in the last situations, this situation, because you cannot put E here, so there is the only way to write here is the A, and therefore E is the last element. So what has to be noticed is that each element is reciprocal to itself. E into E is E, A into A is E, B into B is E, and C into C is E. So each element is reciprocal to itself. So this is the way in which the group multiplication tables of various orders can be constructed, and therefore you can go for constructing these group multiplication tables. However, this knowledge of mathematics to construct a group multiplication table is not very important in the idea of dealing with the group theory and symmetry, and therefore I'll sum up, or finally I would say that if you want to write a group of order 6, then the possibility could be of this kind here as shown in this group multiplication table. And you see here what we do is most of the elements are the diagonal elements to themselves, but D is not reciprocal to itself. Instead, D is reciprocal to F and F is reciprocal to D, and that would make a complete group multiplication table for order 6. So friends, you can construct a group multiplication table using a logic, and the most important logic that comes into mind is there should be no repetition in a row or in a column. This is okay for now. We'll see in the next video. Thanks for watching again. See you in the next video.